Good day and welcome to part one of our discussion on inverse functions. This initial chapter of the semester is purely focused on introducing and reminding you of properties of inverse functions to get started so that we are able to move on to frequently encountered functions that we have not been able to differentiate or integrate in our Calculus 1 experience. Things like inverse trig functions, exponentials, and natural logs. But before getting to these nice calculus results, we do need to go back and review some of the basic properties of inverse functions that we will be utilizing. And with that in mind, if we were meeting in person, face to face, I would be warning you not to be too complacent in the beginning of the semester, because even though it may seem to start off a bit slow, Calculus 2 does have a tendency to pick up rapidly. And in fact, if you were to talk to past students who have completed the calculus sequence, they usually indicate that they had the most difficulty in Calculus 2. And what that tells us is that we want to make sure that we establish good study habits right from the beginning. I don't typically invest substantial time in the beginning of the semester reviewing all of those basic properties from Calculus 1, but you can find a Calc 1 overview sheet located in Canvas, which comes from the EMS Student Success Programs webpage. But at the end of this section, we'll go through several kind of reminder examples in terms of differentiation integration, and I will be very cognizant to remind you of common formulas as we encounter them. But that being said, it's most definitely not a bad idea to go back and remind yourself of, at a minimum, the important differentiation formulas, the common functions we can differentiate, integrate, along with u substitution. So diving into inverse functions, we first need to think of functions in general. And we typically think or view a function as a map that goes from some set A to another set B. The language that we would introduce for these sets is we refer to A as being the domain of the function, that's where the inputs live, and we think of B as being the range, where we find those outputs. And the defining characteristic of a function is that an input only has one output. And a common question encountered, and what we are going to explore in this section, is can we undo a function? And I should be specific as well. And when we ask can we undo a function, it's can we undo a function as a function. And let's look at a few examples to get us started. In the first example, we have a function f that maps from a set containing the elements 1 and 2 to another set containing the elements 3 and 4. The typical notation that we would use is probably familiar. We would say f of 1 is equal to 3, and f of 2 is equal to 4. And we can also think of f as being a collection of ordered pairs in a sense. 1 comma 3 and 2 comma 4. And in the second example, we have a function f mapping the set containing 1 and 2 to the set containing 3 and 4, and now we've just defined it slightly differently. We're going to have 1 map to the element 3, and 2 also map to the element 3. So in this case, we would say f of 1 is 3, and f of 2 is equal to 3. And that is perfectly fine for a function to have two inputs that go to the same output. What would not be fine is if you had an input going to multiple outputs. In that case, it wouldn't be a function. So notationally, once again, we can think of this as being two ordered pairs, 1 comma 3 and 2 comma 3. And let's get back to our question. Can we undo these functions? And immediately by observation, if we look at the first function, you say, yeah, absolutely. We can take 3 and send it back to 2 with the function we might refer to as f inverse. And you can take 4 and you can send that back to 2. So we can define f inverse. So symbolically, it's f raised to the minus 1, but that's not the reciprocal. That's a notation we use for undoing the function f. And we could define that in terms of ordered pairs. 3 goes to 1, 4 goes to 2. And then we ask ourselves the same question with this second example. Can we undo this function f as a function itself? Well, what would such a function look like? You would have to have 3 going to 1 and 3 also going to 2. So in terms of defining f inverse of 3, well, we have no idea how to define it in terms of a function. So the observation I'm going to make is that we cannot undo f as a function. And the key observation is not being able to undo it as a function. And intuitively, we probably see the key issue that does not allow us to do it as a function. You have 2 inputs to the function f mapping to the same output. And what that means is if you try to undo it, that output 3, now as the input to f inverse, would have to go to multiple outputs, which is not allowed for a function. And in terms of some more mathematical language, we would say that this function is not one-to-one, whereas the function above that we were able to undo is one-to-one. So what do I mean by this? A function is one-to-one if it never takes the same value twice. And we can write this a bit more analytically as well. That is, we can say f of x1 is not equal to f of x2, so the function values are not equal whenever x1 is not equal to x2. And if we look at that second example we have above, we can make the observation that it is not one-to-one. And we can also give a reason. And this is what we have to be careful to make sure we're doing. So why is this function not one-to-one? Well, because 1 is not equal to 2, which I think we can all agree on, but f of 1 equals f of 2. So you have 2 different inputs with the same output, so not a one-to-one function. And when it comes to determining if a function has an inverse, one-to-one is going to be the key characteristic that needs to be satisfied. And before defining an inverse of a function a bit more precisely, let's go to a familiar example involving graphs of functions that we've encountered many times in the past. The common example that I would like to investigate and really ask you is the function f of x equals x squared one-to-one. And if we were meeting in person, this is where I would be turning the floor over to you. I would ask you to think about this for 1 or 2 minutes, discuss with your neighbors, and decide, yes, it is one-to-one, or no, it is not one-to-one, and give a reason why it is not. So with that in mind, I'm going to ask you to pause the video, give yourself 30, 60 seconds, and decide upon the answer. And throughout our discussions, I will frequently ask you to pause the video and think about a question, and I'm going to give you the reminder, you will take out of this experience what you put into it. So keep that in mind. Hopefully at this point you've paused the video, you've thought a bit about this problem, and the answer is no, it's not one-to-one. The reason we know that it's not one-to-one is we can easily come up with multiple examples of 2 different inputs that have the same output. For example, -1 is not equal to 1, which is usually the example that students will present, and f of -1 equals 1, which happens to be equal to f of 1. So this is not a one-to-one function. And it turns out it's really easy to determine if a function is one-to-one if you have its graph. Intuitively, if 2 inputs have the same output, that means that a horizontal line will intersect the graph in multiple points. So in this case, our observation was if we look at that horizontal line, y equals 1, it very clearly intersects the graph twice. And in this case, we would say the graph of the function y equals x squared does not pass the horizontal line test. And in fact, the observation or reminder from previous pre-calculus courses is that f is 1 to 1 if its graph passes the horizontal line test. And just to make sure we're all on the same page, by the horizontal line test, what we mean is that no horizontal line will intersect the graph more than once. And I will almost always abbreviate when possible. In this case, I will use HLT for the horizontal line test. And we are now ready to define what we mean a bit more precisely by an inverse function. So if a function is 1 to 1, then it has an inverse. And the notation we use for the inverse is f superscripted with a -1, and it is defined as follows. We say that f inverse of x is equal to y whenever, and just remember intuitively, an inverse undoes the function. So whenever f of y is equal to x. So again, f inverse undoes the function f. And just a few observations to end with. Because f inverse undoes the function f, we can note that the domain of f inverse would have to be the range of f. That is to say, the quantities or elements you input into the function f inverse are the outputs of f. And similarly, the range of f inverse will be equal to the domain of f. And this finishes our introduction into inverse functions. We will carry on this discussion in the next video. But let me finish with just a few reminders I will hopefully continue to give you. This is a perfect opportunity for you to pause and start practicing examples. You can find suggested problems that come from the textbook, mainly odd problems where you can double check your answer in the back of the book. So I strongly encourage you to make sure you're working suggested problems. Remember, you can find the blank and the completed note sheets on Canvas for each of these sections to hopefully aid you in the process of taking notes and viewing the videos. And whenever you have questions, do not hesitate to reach out. Drop me an email, stop by the virtual office hours. I would love to meet you. So stay tuned. Take care.